Day 146, Circuit Analysis 1D. Once again, when I have circuits, the two of the basic principles are that if you have elements that are in series, they will have the same currents, the same flow of charge, different potential differences, different voltages. When you have things that are in parallel, each of those elements will have the same potential difference, same voltage. Here we have a circuit that has some parallel, some series. For example, the 20 and the 10 ohm resistors are in parallel. I know they will have the same voltages as each other. And if the 30 ohm resistor weren't in this circuit, they would each be 100 volts, but they're not 100 volts. Okay, they're each equal to each other, but not equal to the battery voltage. We'll come back to that. And one of the techniques that we use is simplifying the circuits, drawing these diagrams. In other words, the 20 and the 10 are in parallel, so I will use the rule where I do 1 over our total, or our combined, is 1 over 20 plus 1 over 10. If I do the math there, the resistance for those two resistors is 6.7 ohms combined. Draw the diagram. It looks like this. That would be the 6.7 ohm resistor, 100 volts, 6.7 ohms, and then 30 ohms. All right, one more diagram, combine the 30 and the 6.7, that's a 6.7. That gives me my final simplified diagram of 100 volts with 36.7 ohms of total circuit resistance. All right, and then from here on out, we're analyzing the simple diagrams that I just drew, starting with the simplest, applying Ohm's law, V equals IR, which is basically all we'll be doing now for the next 3 or 4 minutes. We have 100 equals I times 36.7. That's 36.7 ohms. And the total current, rounded off to 2 sig figs, is 2.7 amps. All right, that's my battery current. I'll fill that in the table. 2.7 amps. The battery is 100 volts. That's the flow right here. And if I look to the other diagram, the simple diagrams down here, we have a flow of charge, not starting from the battery, but that's the way I started my arrow. But all the charge is flowing all at the same time, starting at the same time, all flowing everywhere, 2.7 amps. So each of these elements, the 6.7 ohm resistor has 2.7 amps of current, and the 30 ohm resistor has 2.7 amps of current, and the battery has 2.7 amps of current. So I know I can fill that in right now for the 30 ohm resistor because that's in series with the battery. It's 2.7 amps. But what is its voltage? Well, I'm going to use V equals IR to calculate the voltage of the 30 ohm resistor. So V equals IR for the 30 ohm resistor, unknown V. V equals 2.7 times 30. So V equals 81 volts. That's my voltage. I'll fill it in the table. 81 volts for the 2.7 ohm resistor. But now this supplemental, or the replacement 6.7 ohm resistor, I can figure out the voltage for that, which would be V equals I, 2.7 amps of current going through that resistor, times the 6.7 ohms. So that gives me 18 volts. And you can sort of check to see if that's correct, because the 6.7 ohm resistor, which has 18 volts, then would be consistent with 18 volts for each of these two, because they're in parallel and they are replaced by the 6.7 ohm resistor, so they're each the same voltage. And if you look at the table, however, the voltage of the 18 for each of those, they're each 18 volts. 18 plus 81 is 100. In other words, you don't add those twice because they're replaced by a single resistor of 18. The 18 volts once plus the 81 is 99 volts, close enough, rounded off. So those are each 18 volts. And then you can use V equals IR to figure out the current now in each of the little resistors in the original diagram, the 10 and the 20. You can do it on your calculator. V equals IR. In other words, take the V, divide by the R, you get 1.8 amps of current in the 10 ohm resistor, and V 18 divided by 20 gives you 0.9 amps in the 20 ohm resistor. Bottom line, once again, what's happening here is there's a current flowing in this part of the circuit of 2.7 amps through all the 30 ohm resistor. That's 2.7 amps. That current, when it comes through the battery's pushing and it gets this spot up here. If I call that point A, and the current wants to get to point B, point A to point B, it splits. Twice as much goes through the smaller resistor. And as you see in the table or the calculations, 1.8 amps goes through the 10 ohm resistor, 0.9 amps goes through the 20 ohm resistor, and it comes back together at point B and combines to make 2.7 amps again. All right, so once again, you just calculate the power by P equals VI or P equals I squared R. The numbers come out to be 32 watts, 16 watts, and 219 watts. A lot of current. That makes that the brightest or most powerful resistor. If it's a light bulb, it's the brightest. And independently calculating the power of the battery, P equals VI, 100 times 2.7 is 270 to 2 sig figs. And if you add, once again, these three numbers, the 32, the 16, and 219, I should get 270. You get 267, but if you round off to 2 sig figs, it is 270 watts. So the power supplied by the battery is equal to the power used or given off, turned into heat or light by the resistors. So there we have it. That's how you analyze these circuits. Please draw the diagrams and then work backwards from the simple diagrams using V equals IR to figure out how much current and voltage there is for each of the elements, following the basic principles of series and parallel and using V equals IR.